Alrighty, guys. Good morning, and welcome again to Year Long College Algebra. As you'll notice, I'm still not quite back in the classroom. I'm still feeling pretty under the weather, so I figured I'd play it safe and stay home just so I don't get anybody else sick in the classroom. The good news is that in the meantime, I've got this video lesson for you, and it should be a pretty quick, straightforward review of a lot of the basics. When we talk about function notation, what it means, how do we evaluate versus solve a function, but we'll also do a little bit of review of solving functions, either graphically or algebraically. So a lot of stuff that you guys have seen from Algebra 2, stuff that you're already probably pretty familiar with in a variety of contexts, but just some extra review as we get into the swing of the material. Bear in mind that you guys have the phone slots in the wooden caddy that you should be bringing your phones up to at the beginning of the lesson. The sub should have a note that says students should be turning in phones. So if you need the reminder for which one is your assigned slot, you're more than welcome to take a look at these here in the slides, and we'll go sort of from there. So if you haven't already, please make sure to bring your phone up to the front of the classroom. And as we get rolling into our lesson for today, I wanted to do a couple of warm-up problems from practice 1-1 and a warm-up problem from the practice for 1-2. You guys will find the practice problems in the note spiral at the very end of each of the sections of notes that we're completing. You should be wrapping up the practice for 1-1 pretty quickly, and you're probably getting through most of practice 1.2 already, if not already done. So as we move along, you want to make sure to be knocking out these as you go. In the practice for 1.1, the goal here is to determine for the relation graph to the right whether or not it's a function, and if it's a function, whether or not it's one-to-one. We're also going to do some analysis of things like the domain and the range. What I want you to do real quick is maybe discuss with the people around you. Is this a function? Yes or no, and how do you know? And is this one-to-one if it is a function? And again, how do you know? From there, maybe talk a little bit about the domain and the range. You can use either interval or inequality notation here, but I want to give you maybe a minute or two just to get the gears turning here, and this will be a good review of some of the big ideas from what we saw in 1.1. So the first thing that we want to take a look at, if we're trying to determine whether or not something's a function, is what it means to be a function versus just a relation. A function is a kind of relation in which for any choice of x, for any choice of input, you're guaranteed only one output, so long as that x is defined, if that x is in the domain of the function. So what that really means is if I choose an x, I can expect only one y. And that's sort of synonymous graphically with something called the vertical line test. So if I think about, say, x equals -1, I'm going to notice here that there's only one output, and it happens to be about -6. And if I choose, say, x equals +1, I get only one output. That's also -6. And if I choose, say, x equals 2, my output there is approximately -3. There's nowhere I can put this vertical line on the graph and get several results out of it. So in this particular instance, it is a function. When a function's a function, sometimes it's also one-to-one. One-to-one is essentially the same argument in reverse. Instead of every input being guaranteed to have only one output, you can think of it as saying every output is also guaranteed to have only one input. So if you think about the opposite of the vertical line test, which is the horizontal line test, what I'm checking for here is whether there's maybe some place on the graph where I can draw a horizontal line for a certain y value and get several inputs x out as a result. And I'll see here, for example, at y equals -3, there's kind of a problem. For this particular function, if I say, hey, the result is -3, you're going to give me several inputs that could potentially give me that result. It could be -2, could be +2, or it could be 0. So given that it's failing the horizontal line test, we know that this is just a function, not necessarily a one-to-one function. And what that means is if we were to invert it, the inverted version of this function would not also be a function. But we'll talk more about that as the year sort of progresses. If I'm thinking about something like the domain and the range, maybe the range is kind of an easier place to start here. We'll notice that this graph goes as low as -7, but it also goes up forever to positive infinity. So my range here might be -7 with the bracket and infinity with the parentheses. It's the domain where sometimes students get a little tripped up. What you'll notice here is that on this graph, there's these two like arrows on the very top of the function. A lot of people interpret that pretty easily as meaning the graph is going up forever. But I want you to also notice that it's slowly going left and right forever as well. Now, if it's slowly going left and right forever, eventually it's going to hit all the negative x's and all the positive x's as well, in addition to all the x's in between that we've already seen from the graph. So is there really an input that this thing's not eventually going to be able to deal with? It's going to hit a little bit of everything, right? Even though it's going to take a while for it to do it. In that kind of a process where even though it's moving slowly, it's still moving forever, it doesn't really matter the speed at which the graph moves. So the domain on this guy is unlimited. It goes from negative infinity to infinity without much of a problem. Now, the next one that I want to go over is slightly more open-ended. We are tasked with drawing on a set of axes, a graph of a function, but we also want this function to be one-to-one. And we want it to have this particular domain in range. If you haven't already, I want you to take a look at this problem with your group mates, and I want you to discuss it for maybe a couple minutes. Given these conditions, what is perhaps one graph that we could draw that's going to capture all of these behaviors? This might be a little trickier than you think at first, but we'll kind of go over this in just a minute. All right. So what I've got is a problem where there might be more than one solution. All we're tasked with doing is drawing a graph so that it's a function, which means it's going to pass the vertical line test, which means for any x, there's only ever one y, but we also want it to be one-to-one, which means in reverse, for every one y, there's only one x. So that means I have to draw something in such a way that every x has a y and every y has an x. So it's going to pass both of those tests anywhere in the domain. Now, the other thing that they tell us is that the domain is going to be limited. It's going to be limited from x equals -2 up to x equals +5. So what I'm going to do is just sort of draw in these boundary lines. I'm using this sort of like hashed vertical line here. These are mainly just telling us that I need to operate between those when I'm drawing my graph. I'm going to do the same thing with the range. I need to operate between a y value of -1. So I'll draw in like my lower boundary here and my upper boundary of y equals 3. So inside of that sort of rectangular region in the center of my graph, that's where I need to draw this thing. And I've got to draw it in such a way that there's no overlap for x's giving y's and no overlap for a y giving several x's. Now, this one kind of requires a little bit of thought, right? In the domain, I've got to draw something where the input -2 is not defined, but the input 5 is. And for the range, I've got to draw something where the output -1 is defined, but the output 3 isn't. So that bracket means I need like a filled in circle. I can be that value. And the parenthesis means that I need to use an open circle. I have to exclude that value in the particular interval. So it might take a little bit of thought, but what I want you to notice is that there's at least one graph that we can draw that meets this criteria. What I could do is draw an open circle at the coordinate -2, 3, so that that domain value of -2 and that range value of 3 is not defined, but it's like a boundary. And over here at x equals 5, y equals -1, I can draw a filled in circle so that that value is defined. Now, I've got to connect this up with a function that's continuous because I've got to hit all the x and the y values in between, but there's not necessarily just one way I could do it. Maybe the simplest way would be to draw kind of like this linear function that's just sort of going straight between these two coordinates. But you could also maybe draw some kind of decreasing function that's nonlinear, so maybe it's sort of exponential or rational there. You could draw it maybe decreasing from above there, so it's kind of got this like upward arc to it. There's not just one correct way to do it. What I would probably say is that this first thing that comes to mind for me is this nice decreasing linear function. But if I take a look at it, I'm passing the vertical line test for any input that I choose. I'm also passing the horizontal line test for any output that I choose. So this is kind of the simplest answer that I could potentially give, where I've met the definition that this is a function. It's also one-to-one, and it's also meeting the criteria for the domain and the range. So kind of an interesting little example there. It asks us to do a little problem solving to try and determine how to get this done. The last one that I want to hit is this practice problem from section 1.2. Here in 1.2, I've got a graph drawn to the right, and I'm trying to write the equation that would give me that graph. It's kind of the opposite process to what we practiced in the notes for 1.2. One thing that I think might help here, as far as kind of like a structure to solving this problem, is to discuss with your group mates in this order these different questions that might be popping up in your mind. What family of functions generally would you say this graph belongs to? What would the parent function for that look like without any transformations present? And then how is this graph transformed from that parent? And then use those details to kind of write in the equation template at the bottom of the slide and in your practice. So I'll give you maybe a couple minutes to think this one over with your group mates. What family of functions does that graph in red look the most like? What parent function would best fit that scenario? And what transformations happen to that parent function to get this guy as a final result? So if I take a look at this particular function, what I'm going to notice is that this guy is a quadratic function of some kind. It's a parabola in the sense that it's got like this axis of symmetry at x equals 3. The range is going up to infinity in both directions, to the left and to the right. It's got a minimum value at -4 in the y's. So I know that this is quadratic. When I think about quadratic functions, I know the parent function without any transformations present is just y equals x to the second. Now, some transformations have occurred to get that guy to look like this guy in red. But what I want to emphasize here is that if you're thinking about just, say, a set of coordinates for what the quadratic function used to look like, you might test inputs like -3, -2, -1, 0, 1, 2, and 3. If I do 0 squared, I get 0. If I do 1 squared or -1 squared, I get 1. If I do 2 squared or -2 squared, I get 4. And if I do 3 squared or -3 squared, I get 9. So what I'm going to do is just sort of mark on my graph what the parent function used to look like. And I'm going to sort of use that as contextualize what I'm seeing on this graph in red. And that might help me iron out what transformations have occurred here to go from that parent function to this version that I see here. Now, what you'll notice is that there used to be a coordinate at the origin at 0, 0. That's also where the axis of symmetry for this parabola was passing through. If I take a look at my graph in red, that's shifted. It's now at the coordinate, in this case, 3, -4. So it's gone right 3 units, and it's gone down 4 units. So I'm just making notes of that, and that's going to help me identify like my A, my H, and my K transformations. The other thing that I want you to notice is that from that center point at 0, 0, usually I went left or right 1 and then up 1 to get to my next set of coordinate values. If I take a look at my parabola drawn in red, I'm going to notice that I go left or right 1 from that sort of center point, but I have to go up 2 units instead of just 1. From my sort of first third coordinates on the parent function, I go left to right and then up 3 to get to my next ones. For this guy in red, I'm going to notice that I go left or right 1 and then up 6 to hit my next set of coordinates on the lattice point of the grid. So what I want you to think about there is how many times faster is this graph moving? It's moving twice as fast. So there's a vertical stretch by a factor of 2. And if I identify these 3 changes, that's going to allow me to figure out the transformed version of my quadratic function. So maybe the first thing that I'll do is I'll sort of write in the fact that I know that this guy's quadratic, so I'm going to have x minus blank squared. But I'm also going to have like this plus blank space on the outside for the k transformation, and I'm also going to have a space at the front there to multiply it by my a value. So to sort of fill in the missing pieces here, if I want to go right 3 units, I'm going to have to write an x minus 3 in the parentheses. It's the opposite of what I think. That one's kind of tricky. I'm going to need to do a 2 times this quantity on the front to get it to go up twice as fast. And then for my k term, if I want to go down 4 units, I might write minus 4 here instead of plus 4. So we're practicing geometric transformations. We're just kind of doing the backwards process for what we saw in the notes. We started by identifying the family of functions. We identified the parent function for that family, and we used that to compare and contrast and say, okay, what is this graph in red looking like? What transformations have I observed? And we use that to write the final equation. You'll see a handful of those in that practice as we go, but I wanted to go over that just to kind of get the gears turning and recap and review. Today, we're going to move pretty quickly through a video lesson for 1.3. There's not a whole lot of new or surprising topics in this lesson, so it should move pretty fast. Last 20 or so minutes of class, you guys will iron out the quiz for 1.1, 1.2. It should also be fairly quick and straightforward. There's not a whole lot of new material there. A lot of what we're covering in the beginning of Unit 1 is a lot of basics that you guys were practicing back in Algebra 2. We're going to wrap up Unit 1 about September the 5th or the 8th, depending on whether you're an A-Day or a B-Day student. Our Unit 1 practice assignments are going to be due by September the 8th there. In addition, if you need to check out a graphing calculator, for those of you guys that are in my A-Day sections, you should have some time to do so in class. The sub might have copies of the calculator checkout form. Before you guys go to check out calculators, if you fill that out beforehand, it'll help speed up the process a little bit. But at the end of the day, if they don't have that form, that's okay. When you go to the MRC, they should have some extra copies there as well. So don't panic. There's no rush necessarily. Otherwise, as we go, we'll start moving into sections 1.4 and 1.5. Hopefully, I'm going to be back by Wednesday or Thursday of this week, but again, we'll play it by ear. I don't want to get anybody else sick just because I'm not feeling well. So today, we're going to review how to utilize function notation to both evaluate and simplify, but also solve algebraic expressions. We're also going to review how to solve equations both graphically and algebraically. When we talk about functions, we know that a function says for any input, there's only one defined output. What we are practicing in 1.2 is recognizing that there's a lot of basic patterns or families of algebraic functions. We saw in our last slide show for 1.2 or last video lesson that there's these larger families that things are sort of fitting into. They could be linear or nonlinear. Of the nonlinears, they could be quadratic or cubic, they could be square roots or cube roots, they could be rationals, exponentials, logarithmic. There's quite a handful of them, but there's usually a certain family that a given function is going to fit within. By recognizing the family of functions, we can recognize that transformations on that parent give us an infinite number of variations of that pattern. And we have this sort of like general template here for A, H, and K on the geometric transformations, which predictably do the same things every time. So if you know the basic pattern of behavior and you understand geometric transformations, you can graph any function by hand in this case, if it belongs to one of these larger families. As we go, what we're going to start to focus on a little bit more is this function notation. When y is a function of x, we often say that y is equal to f of x, and they're kind of interchangeable. But what I want to talk a little bit more about is what that means, say, when we're evaluating or solving. So in the notes today for section 1.3, you'll notice that you're given a graph shown here to the right on this slide, where we're asked to evaluate f of 3, and we're asked to find x when f of x equals 2. When we are asked to find f of 3, that is evaluation. What you'll notice in that notation is if y is equal to f of x, and they ask us for f of 3, we switched out x with 3. So if x is equal to 3, essentially what they're asking there is for us to figure out the corresponding y value. So to do that graphically, what I'm going to do is go over to x equals 3, and I'm going to find the corresponding coordinate on the graph and read off its y value, which in this case is -1. So if I wanted to evaluate this function for an input of 3, I would say that f of 3 is equal to -1 using this notation. Now, if I say, let's find x when f of x is equal to 2, that's a little bit different. F of x is equal to y. They're interchangeable. So when I say f of x is equal to 2, what I'm saying is when the output is 2, what's the corresponding input? So I find on my graph the coordinate that corresponds to y equals 2, and I read off the input for which that occurs. So in this particular instance, I might say that x is equal to approximately 7.5 when f of x is equal to positive 2, and that might be my final answer. So that is essentially what we mean by solving a function or solving an equation. If we want this desired output, what's the input we need to get it? Evaluating and solving is something that we're going to do all the time in year-long college algebra, so it's nice to kind of recap and review the notation here, but this is how you do it graphically. You've probably gotten a lot of practice with this algebraically, but I wanted to really hit the concept of this, and we'll start to talk a little bit more about that as time goes on. So try this maybe real quick. If I give you this graph and I want you to evaluate f of 6 or f of -5 halves, or I want you to solve f of x equals -5 or f of x equals 1, what are some of the values you're going to get as responses? Should only maybe take about a minute, but with your group mates, using the graph, I want you to find your answers. All right, so if I'm looking at my function, which in this case is a linear function, and I wanted to evaluate f of 6 or f of -5 halves. This keyword of evaluate means that I'm using a given input and I'm finding an output. So when I say evaluate f of 6, I'm saying for an input of 6, what's the corresponding output? And I'll see in this case that f of 6 is equal to 1. That's the y value. If I wanted to evaluate f of -5 halves, which is the same thing as -2.5, what I'm going to do is go to -2.5 as an input. I'm going to try and read off as close as I can the corresponding output, which in this case appears to be -4.5. Or I could say that that's something like, would that be like -9 halves? I think it is. Now, if I'm solving, that's another keyword. And in this context, when I say solve, what I'm saying is here's a y value, work backwards to find an input. So if I go to a y value of -5, and I read off the corresponding input for that, I'm going to see that f of x equals -5 when x equals -3. And if I want to solve, say, f of x equals 1, well, that happens when x is equal to 6. So really all we're doing here is just kind of swapping the process. Evaluating says for an input, give us the output. Solving says for an output, give us the input that gets you where we want to go. If you're thinking about this a little more algebraically, what you may have recognized is that for this linear function, you've got a y-intercept of -3, and you have a slope of something like 3 halves. So you may or may not have noticed that this guy's going to be like 3 halves x minus 3 in this case. If you're working the problem this way, and my slope is actually 2/3, not 3 halves there. Let me fix that real quick. There we go. My sick brain's kicking in. You can sort of check your solutions to this particular instance. So if I wanted to evaluate, say, f of 6, I could say that y is equal to 2/3 times 6 minus 3. 2/3 of 6 is going to be like 12 over 3, so that's like 4 minus 3, and I'll see here an answer of 1, which is exactly what I got graphically, so I know I'm on the right track there. I could even solve this equation algebraically by saying, hey, when y, or f of x, is equal to 1, then I'd say 2/3 x minus 3 is equal to 1, and I can solve it this way too by just reversing the order of operations. So I'd add the 3 over, so I've got 4 equals 2/3 x. I can then multiply by the reciprocal on both sides, so multiply both sides by 3 halves if you want. Another way to do it is to multiply both sides by 3 first, and then divide by 2, and kind of take it one step at a time there. But what you'll get in this particular instance is that x is still going to be something like 6 in this case. So either algebraically or graphically, I get the exact same thing. So no surprises there. These are skills that you guys have practiced a lot already in Algebra 2. We're just sort of reviewing them as we go. So here's another one. Let's say h of x is this function. I want you to evaluate at some of these inputs. So maybe pause the video, take a couple minutes, and try giving these a go. All right, so once again, we are doing evaluation in this case. And we know evaluate is a keyword that says for this given input, find the corresponding output. So if I'm thinking of, say, h of 5, that means my input is 5. And everywhere I see an x, I'm going to substitute that in, and then I'm going to simplify to get my answer. In this particular instance, if I plug in a 5 here, I'm going to see that I'm taking the square root of 5 to the second minus 9. And if I'm simplifying, what I'm going to do is follow the order of operations here. So I'm going to do parentheses, exponents, multiplication, division, then addition, subtraction. You can think of parentheses as being any sort of grouping symbol. So I'm going to do everything under the square root first and then square root it. Underneath the square root, I've got to do 5 to the second. So I'll do 25 minus 9 first there. Now, if I do 25 minus 9, that's going to be like 20 minus 4. That's going to be like the root of 16. If I take the square root of 16, one thing you got to be careful about is there's really two answers. The first answer that might pop in your head is positive 4, because 4 by 4 gets you back to 16. But you could just as easily do negative 4 as well, because negative 4 times negative 4 also goes back to positive 16. So I'd see in this particular instance that those are my two outputs for this given input. If I wanted to evaluate h of 0, what I would do here is just plug in 0 for x. So I do the root of 0 squared minus 9. I do everything under the grouping symbol first. 0 squared is still nothing. So I'd be trying to take the square root of negative 9. Now, if you're trying to answer the question, what times itself is still negative 9, and you're thinking only of real numbers, this is where you maybe run into a bit of a headache, right? There is no such real number that multiplies by itself to still be negative. What you could do here, though, is say that instead of a real number, it's an imaginary number. So if I take the square root of 9, I'd get plus or minus 3. So in this particular instance, the square root of negative 1 is what we define as I. So I could break the root of negative 9 into the root of negative 1 times 9, and then I could do the root of negative 1 times the root of 9, and that's how we got that complex value. You should have seen that in Algebra 2. If you haven't quite seen that recently, if that's feeling a little wonky, I wouldn't panic. We'll continue to review imaginary and complex numbers as time goes on. It's just kind of a nice little Easter egg here. On, say, this third one that I want to do, h of the root of 12, what we're going to do here is plug in the square root of 12, raise that to the second, subtract 9 from it, and then try and take the square root of it. In this particular instance, if I do the square root of 12 times itself, if I raise it to the second power, then the square root and the square are going to kind of cancel each other out. And that's going to leave me with just 12. So now what I'm going to be doing is the square root of whatever 12 minus 9 is. So in this case, 3. But there is no number, at least that I can think of off the top of my head, that multiplies with itself and becomes 3. So this one is also going to be sort of irrational, right? It's not going to be a nice whole number. In this instance, I might leave it as just plus or minus root 3. You can pop that into a calculator. You'll get an irrational decimal out of it, but we know that there will be two values for it. For something like h of 4, it's the same process. Plug in the 4, you get 16. 16 minus 9 in that case is something like 7, if memory serves. So you take the square root of 7, which is irrational, and your answer is plus minus 7. So no surprises there as far as that last one. Here's another one. G of x equals 2x squared minus x. With the group mates, try evaluating. What you'll notice here is that sometimes they say evaluate and sometimes they say simplify. They're kind of synonymous. The wording is not exactly the same, but the process is identical. Evaluate, we usually take an input in there and then simplify. Simplify is kind of jumping the gun and saying for this input, go ahead and reduce it down. What you'll notice is that it's starting to get a little more complicated. So maybe what I'll do is 3 of the 4, and I'll cover more of the algebraic expressions instead of g of negative 3. But you guys try this one real quick. So in this particular instance, I've got a function g of x. It's some kind of quadratic equation because I've got x to the second. It's just not written in vertex form like we see with transformations. In this case, it's written in something more like standard form. What I want to do is evaluate or simplify for a given input. What you'll notice here is that some of these inputs are not just numbers. Some of them are full-on algebraic expressions. So I'm going to focus on these three because I think you guys can deal with g of -3 just fine without me. Let's say that we wanted to focus on maybe this top right guy first, this g of 4t to the third. X is our independent variable, and here x is being swapped with this full expression. So what we're going to do is the same process. It's just here I'm going to say that instead of 2x to the second, I'm doing 2 times 4t to the third squared minus 4t to the third. So the procedure is no different. It's just a little bit more of a complex simplification that I'm doing. Now, 4t to the third to the second power is essentially saying take 4t to the third and multiply it by itself. So if I'm thinking about 4t to the third times 4t to the third, the 4 times 4 is going to give me 16, and then t to the third times t to the third might require me to review my exponent properties, and that's going to look like t to the sixth. If I'm multiplying the same bases, I can take the powers and I can add them. So 4t to the third squared is going to look like 16t to the sixth. So I can simplify this to be like 2 times 16t to the sixth minus 4t to the third. Then I can take that 2 and multiply it onto 16 and get 32t to the sixth minus 4t to the third. And that's about as simplified as it's going to get. I could maybe take a GCF of 4t to the third out of both of those so that it's 4t to the third times an expression. But it doesn't really help things, right? It's not a wrong answer. It's just kind of equivalent. So I might leave that one be just the way it is. Let's maybe tackle this guy in the lower left-hand side. I've got g of x plus 2. So here, instead of 4t to the third, where I have a whole different variable, I'm doing x still, but I'm doing x plus 2. So what I'm going to do here is I'm going to rewrite g of x, but everywhere I saw that original x as a placeholder, I'm going to swap it with x plus 2. And from here, I'm going to need to think about how to simplify this down. Now, you've got to be really careful with x plus 2 to the second. Every year that I've ever taught math, anything that's involved algebra in some way, I've always got students who think that x plus 2 to the second can be rewritten as x squared plus 4. That never, ever, ever works. What that student is thinking of is just distributing the powers. It will never, ever, ever work. In fact, it's so common of a mistake that it has its own name. We call this the freshman's dream. If the freshman's dreams were true, then Algebra 1, let alone the rest of algebra, would be a lot simpler than what it actually is. It just doesn't work that way. Instead, what you want to think about is something like x plus 2 itself as a quantity. X plus 2 has two terms. It's the x and the positive 2 term. It's multiplying by itself. So what you can think about here is, depending on how you've been seeing this, foiling these two terms together, where you do first times first, you do first times outer, you do inner times inner, and then you do last times last. Or, in my opinion, something that's a little more efficient is you use an area model, a little 2x2 multiplication chart. X times x is x to the second, and 2 times 2 is 4. But notice the freshman's dream fails because it forgets to do the other two multiplications. I've got x times 2, and I've got that happening twice. So when I add everything together in that area model, it's not just x squared plus 4. It's a little more complicated than that. So as I simplify this down, x plus 2 to the second is like x squared plus 4x plus 4. I'm also going to distribute this negative here just to kind of get that step done. And then I can distribute my 2 to these three terms in here, this trinomial expression. So now I've got 2x squared plus 8x plus 8 minus x minus 2, and then I can simplify like terms here to get my final answer. I got 2x squared plus 7x plus 6. And that's about as good as it's going to get. That one's kind of tricky. You got to be really careful there with the freshman's dream. You don't want to make that mistake. Every year people do it. It's very tempting, but it just doesn't work. This last one in the bottom right is kind of an Easter egg in the sense that this is something you're going to see a lot more of if you move towards like a pre-calculus or a calculus class. This particular type of fraction where you see like g of x plus h minus g of x over h is something called a difference quotient. And it's a really, really, really important thing for understanding and defining something called a derivative, which again is a calculus topic. It's something that's going to happen a little further down the line for most of you guys, but we can handle this simplification now using only what we understand about algebra. If I see g of x plus h, I'm going to take my function for g of x and I'm going to rewrite it so that everywhere there was just an x, I'm writing x plus h now. And then I'm going to subtract from it g of x. So I'm going to subtract from it 2x squared minus x. And notice that I put that in parentheses because I've got to lose both of those terms. It's going to be like I'm distributing that negative. Now, if I see x plus h squared, I've got to be careful here, right? Because that's not just x squared plus h squared. It's a little more complicated than that. You could think of foiling those together, or you could do x plus h times x plus h in a little 2x2 multiplication chart. You will see an x squared and an h squared, but you'll also see 2xh in that product. So be very careful. I'm also going to take 2 times that result. So I'm kind of running out of room here. I'm going to maybe rewrite or erase my response for, say, this top right corner, just so I buy myself a little bit of room. I'm going to start writing out my answer there for my bottom rightmost problem. So I'll have, say, this kind of area in the corner of the screen that I'm reserving, 2 times x squared plus 2xh plus h squared minus x minus h minus 2x squared plus x, all in that crazy numerator of that fraction, and it's all over h. So I just distributed a negative twice. I just simplified down that x plus h squared term. And then all I'm really doing here is distributing the 2. So I'll have something like 2x squared plus 4x plus h squared minus x minus h minus 2x squared plus x in that numerator, all divided by h. What I want you to notice is that there's some cancellations that are going to happen here. 2x squared and minus 2x squared are going to cancel each other out. Minus x and plus x are going to cancel each other out. From there, you're going to have, in this particular instance, missing an h term there on that 2x there and this 4x here. There we go. Only things in that numerator that have an h in common. So I'm going to clear a little more room down here in the bottom right corner of my slide. I'm going to continue to rewrite as I go here, just make this a little easier to see. So I've got 4xh plus h squared minus h all over h. Notice that I can factor an h out of every term in that numerator as a GCF. And if I do that, I'm going to notice that this h divided by h term is going to cancel out. So my final answer for this crazy problem, right, this sort of Easter egg problem, is just the response 4x plus h minus 1. It's nice algebraic practice. We're going to see this on occasion in year-long college algebra sort of as an Easter egg, just to work those algebraic muscles. The application of simplifying down this kind of difference quotient is going to happen as you move closer to a calculus course. So really the purpose behind this is kind of obfuscated for the time being, but we can still work with it algebraically using only what we know from our last year's math course. So that may have seemed like a lot, and it certainly was, but that's how you kind of proceed through that. What I want you to notice is that we've done just a lot of algebra review here, right? Now, the final thing for our lesson today is sort of recapping solving equations, either graphically or algebraically. If I told you that there's an algebraic equation here on the board, and I wanted you to solve it. There's a lot of ways that you might be thinking about how to approach this guy. If you were thinking about it algebraically, maybe what you do is you square both sides, you rewrite it as a quadratic in standard form equal to 0, and then you think like a factoring strategy or maybe the quadratic formula. But what I want to emphasize here is that if you're trying to solve this graphically, there's a different way to do it. When you're trying to solve an equation graphically, what we want to do is treat each side of the equal sign as a separate y equals graph. So I'm going to break this problem down into being one graph in red, which is the square root of x plus 3, and another graph in blue, which is just y equals 2x. Now, I'm going to graph both of those on this chart on the right. Y equals 2x is a linear function with a y-intercept of 0, so I start at the origin and go up 2 over 1. The square root function starts at the origin, but it's going to go left 3 units, and I graph that using the pattern of transformations for a square root function. Once you get past that and you have the graph, here's what I want you to think about. What is it on the graph that you're looking for to help you find a solution in this case? When we take these two expressions and set them equal to each other, we can do that because they're both equal to y. So really, what is it on this graph that we're using to solve this equation? We're trying to find a location. And in particular, we're looking for an intersection where we want that x value for which it occurs. So these graphs are both equal to each other at 1, 2, but it's that value for x equals 1 that makes it happen. And if you plug it into the equation, the square root of 4 is 2 or negative 2, depending on how you look at it. 2 is equal to 2 times 1, so x equals 1 does yield a valid solution in this case. So anytime you're solving an equation, anywhere in algebra, no matter how simple or how complicated it is, you can use this sort of process to think about getting your solution. It's a really powerful way of checking your work and making sure that your algebra is on the right track. So we'll wrap up with these last two examples in the notes. I want you to solve both of these graphically, and then maybe if you've got a little extra time, go ahead and try and solve them algebraically as well. I want you to solve them graphically, though, without using a graphing calculator. I want you to try and graph them by hand, just to practice that skill of identifying the geometric transformations, and then take it from there. So pause the video, take a moment with your group mates, go ahead and try this real quick. What you're looking for is an intersection. And if there's an intersection on the graph, you want the x value, and that's going to be your answer. All right. So you've taken maybe a minute or two to try your hand at graphing these guys. And the idea here is that if I'm trying to graph these guys by hand, I might want to identify what the parent function is so that I can identify the transformations of that parent function and then go from there to figure out what the graph ought to look like when I'm trying to put it down by hand on the right-hand side. I'm going to highlight each side of the equation, and I'm just going to list a description of that, the kind of general family of functions that it fits in. In the top row there, I've got a quadratic equals a linear function. In the bottom row, I've got a square root equals a quadratic function. I'm going to graph maybe this top guy first. Now, a quadratic function in red usually starts at 0, 0, goes right, left 1, up 1, and then goes right, left 1, and then up 3 all of a sudden. So I've just put down those patterns there from a table of values of x and y equals x to the second. If I see this minus 2, I know that all those coordinates need to go down 2, and if I see that minus 3, all the coordinates need to go right 3. So I'm going to use those to just sort of shift these coordinates around so that I know what the final graph ought to look like. So the x's are the original parent function's graph, and then from there, the solid red dots, those are going to represent my final quadratic for the red highlighted portion. So I've got my quadratic graphed, and what I'm now going to do is the same process for graphing that blue function, 3 minus x, which is linear. My y-intercept in this case is 3, and my slope is just negative 1. So that one's maybe a little bit easier to graph. What I'll notice right off the bat is that as I'm just sort of putting down my coordinates, I get an overlap at two locations. So this equation is not just going to have one solution, it's going to have two of them. And what I want to record is the x value at which those solutions exist. So I'm going to notice that these things are equal when x equals 1 and when x equals 4. And we'll see that those are solutions to this particular equation. Now, I'm also going to do the same process for my equations down here at the bottom. So I'm going to sort of clear away my graphs here and repeat the process. For a square root function, if I were to think of like y equals the root of x, normally that starts at 0, 0, and then it has a coordinate at 1, 1, but then I've got to jump to 4, 2 to get the next one, and then 9, 3. If I see that 2 on the outside, that means I'm going to take these coordinates and go up twice as fast as usual. So instead of going up 1 at a time, they're going to go up 2 at a time. So I'm going to have something that looks kind of like this guy, right? My next y value for 9 is going to be at y equals 6. And that's roughly what that square root graph is going to be. For this guy in blue, it's a little more interesting because I know it's quadratic. So it normally starts at 0, 0, and then 1, 1, negative 1, 1, and negative 2, 4, positive 2, 4, and then negative 3, positive 3, x's yield a y value of 9. This plus 1 means I go left a unit. This random 6 at the front means I'm going up 6 units because it's not multiplied on the parentheses. And I've got this a value here of negative 1. So I've got 3 transformations. I'm going to do the reflection first. So these two coordinates at negative 1, 1 and 1, 1, I'm going to turn those upside down. These coordinates at negative 2, 4 and positive 2, 4, I'm going to turn upside down. So they're at negative 2, negative 4, positive 2, negative 4. I always do those first because once you start translating and moving stuff around, the reflection gets kind of tricky to think about. Now I'm going to take everything left a unit and down 6 units. 2, 3, or up 6 units rather. Left a unit and up 1, 2, 3, 4, 5, 6. And that's going to give me my final graph for my quadratic. What I'll notice here is that I'm only going to really get one solution. In this particular instance, there's only one place that the graph of this quadratic function is going to intersect that square root function, and it's at this coordinate 1, 2. I want the x value associated with that, and that's my final answer. Now, if you wanted to check your work, you can plug these x values into their corresponding equations, and you should get the same number on both sides. So if something is equal to itself, which is a true statement, you're on the right track. As extra practice, you can totally go ahead and try and solve these algebraically. It's really good practice and review of some of the strategies that you saw in Algebra 2, but I wanted just to kind of go over this concept of what graphing and solving looks like. It's a really useful skill to check your work as you go. So with that, that wraps up our video lesson for our time today. As you guys get ready for moving to some work time, checking out calculators, we're going to tackle our quiz here, maybe the last 20 or so minutes of the class. From there, I'm hoping that I'm feeling better soon so that I can join you guys in the room and kind of check in and see how you guys are moving with the material. But otherwise, I hope you guys have a great rest of your day. I hope to see you guys again very soon, and I wish you guys the best of luck on your quiz. Also bear in mind that you have the practices for 1.1 and 1.2 coming up. You should have everything you need to start the practice for 1.3. Otherwise, have a great rest of your day. I'll see you guys again very soon.